Basically, what I'm just trying to say is that when we want to relate that of the square of the peak value to that of the root mean square current, it is simply just let me just do it simple so that it will make it distant. So we can relate this one. The root mean square value is equal to the root of the squared of what do you call it? The root of the squared of this I all over 2. That's what basically it means. And this helps us to get a certain common number because this is a squared. So definitely this and this will cancel. So basically we are going to get something like this. I'll explain into details, don't worry. I'm going to get something like this because this will cancel this, but it will be all over root 2. All over root 2. And so if you want to relate the root mean square in terms of relating it in terms of what we call it, the peak current, then we can say that the root mean square value, the root mean square current is equal to 1 all over root 2, 1 all over root 2 That means when the question says that find the root mean square current given I naught or given the peak what do you call it? Given the peak current to be maybe 2, then that means you multiply the peak current by 1 all over root 2. Now 1 all over root 2 is the same as 0.7 0.707. Yeah, then the same thing applies to that of the voltage VRMS. Sorry, this is IRMS. Now with VRMS2 is the same thing. That's relating that one to the root mean square voltage or potential difference is also equal to this point, this 0.7 V naught. Now, what the short and tall of everything we are doing here means that the root mean square current would dissipate or will give the same amount of heat as a constant. It will give the same amount of heat as the constant direct current with the same magnitude. And so the root mean square current will dissipate the same amount of heat that this I naught will dissipate. Basically, that's what we're trying to mean. Basically, that's what we're trying to mean. Now we know that V is the peak voltage. That means the voltage it reaches before it falls. And VRMS is the effective current, or if it is V, the effective voltage. So relating the effective voltage in terms of the peak current. In other words, it is more like relating the resultant voltage in terms of its peak current is equal to this by that. Basically, that's what we are trying to mean. And it was found by using the averages and so on and so forth. That is not really very necessary. And so that is it. So relating the relationship between this and the peak current is this. And the relation between the root mean square voltage and that of its peak voltage is this. And this they are constant. They are constant. So let's just do some example. Calculate the peak voltage. Calculate I, the peak voltage. I, the peak current. I. Period of an AC current of mains 240 volts, 50 hertz, if the total opposition is 40 ohms. Calculate the I peak voltage, II peak current, III period of an AC current of mains, period of an AC current, period which is time, T of an AC current of mains 240 V, 50 hertz, if the total opposition is 40 ohms. And so let's do it. Yeah, hello.
Please repeat the question.
Calculate the I. Okay, calculate the I peak voltage. I peak current. Calculate I peak voltage. I peak current. I. The period of an AC current of mains. The period of an AC current of mains. 240 volts, 50 hertz. If the total opposition is 40 ampere. If the total opposition is 40 ampere. Are we down? Are we there? Are we there?
Yes, sir.
Yes.
So the question is you should first find for the peak voltage, the peak current. Then we should find for what do you call it, the period. Given given V to be something 250,
240.
240, and given F to be 50. Given V to be V is equal to 240. V have been given F to be 50 50 hertz. Then we've been given R to be, the opposition is resistance, so resistance to be 40 ohms. And the question says you should find for the peak current. Now you bear with me that looking at this, the peak voltage will be V. Hey, looking at this, the VRMS, which is the resultant voltage. In other words, the root mean square. And I said the root mean square is the same as the resultant, or the, in other words, the effective voltage. Or to our lame person, the total voltage. Are you getting it? So VRMS is equal to our 240. Now the question says you should find for the peak voltage. And so our peak voltage VRMS is equal to our I naught. Is equal to our I naught. It's equal to our I naught. Sorry, V naught. 0.707 V naught. Please, do you get it? We know this formula. But the question says you should find for the, but we know that the V naught is our peak voltage. So to find for the V naught, what do we do? So our V naught will be equal to our VRMS divided by 0.707. What are you getting? This is not difficult. When you're doing the theory, it seems difficult, but it's not difficult. What are you getting? But we know our VRMS is 240 volts. What are you getting, please?
Sir.
Yes.
339.4625.
So 339.4 some, so let's say 339 volts. Now the question says we should also find for the peak current. But here we weren't given the current, but we were given the volt, the IV. We were given V, and we've been given resistance, and so we know that VRMS is the same as equal to, according to Ohm's law, RMS times our resistance. That's mathematical expression we know according to Ohm's, but we know VRMS is 240. So this will be 240 is equal to IRMS multiplied by our R. What is our R? Our R is 40. So let's find for I. What will be our IRMS?
6.
That will be what? 6, eh?
Yes,
So
sir.
that will be 6 ampere. So now we can find for our peak current. Our peak current will be what? I naught is equal to 6 divided by 0 point. Or so I naught will give us, what are we getting?
8.4865.
8.48, eh? 48. So let's say that. So let's say 8.5. Now the question also says that we should find for uh, the period given the given this. But we know that period, we can relate period in terms of what do you call it, the frequency, because we know that period T is equal to I all 1 all over F. I hope you know this formula.
Yeah.
So T will be equal to 1 all over F. What the F, we're giving F to be 50 hertz. 50 hertz. What are we getting? What are you getting?
0.02 seconds.
0.02 seconds. So that is it. You see, it's very simple. So basically, that is it. The terms are just there to scare you. When I say, and I'm just telling you that I always don't want to confuse you. I want to use the simple terms. When they say RMS, but it is very expedient that you know this term, so that anywhere you find it. There was one exam they are writing. Don't just write effective distance. Don't write this one because we are talking about alternating currents. If we were talking about direct current, we would have been using the effective current, effective resistance, and so on and so forth. That is what normally then writing RT in some books, effective resistance, when we are doing the parallel connections and those things. But here, because it's a sinusoidal, that's why we are talking about the peak current. That's why we are talking about the effective current. Are we there? But here, the effective current, we are calling it how do you call it, root mean square current. Do you get it? Hello.
Yes, sir.
So basically that is it. Can I please clean the board? Let's do phasor diagram. Phasor diagram. Phasor diagram. Please write it. When you're done, let me clean the board. When you're done, please tell me so that you can continue.
Sir, please, I'm done.
Okay. So let's do. Are you all done? Are you all done too?
Yes, sir.
So let's do phasor diagram. Phasor. Phasor diagram. Now, when we say a phasor diagram is a vector diagram. It's a vector diagram. You know what a vector diagram is? Those of us who have done vectors, I think all of us have done vectors. You know how this thing is. It's a vector diagram which is used to analyze AC circuits. It's a vector diagram that is normally used to analyze AC circuits. So they are used to analyze. When we say analyze, you understand. They are used to analyze AC circuits. So to know that is, it is normally used to know the phase difference and the magnitudes of the current and voltages. And so they are used to know the phase difference, the difference in phases, phase F-A-S-E, and the magnitudes of the current and the voltage. So it helps us to know the difference in the phases and the magnitude. When we say magnitude, the size of the currents being churned out and the voltages. So the phasor diagram is a vector diagram that is used to represent, let me put it that way, or to analyze the circuits, the AC circuits. So for instance, if you have an AC circuit, when they are all resistance, when they are all this, or if it has all the combination of resistance, inductors, and this thing, we have that phasor diagram that is normally used to what do you call it, to analyze it. So when you do data analysis, you realize that it is more or less like when you're doing statistics graph. A graph is used to analyze a specific or a certain data or a certain group of data. So if here it is, if and as if you are talking about histogram, when you know how histogram is, so immediately you see the histogram and the data on it, you should be able to know that, okay, looking at the histogram, you can see that the highest one is the highest mode or something. You should know that the least one is this. You should be able to use the formations on the diagram to be able to get your mean, to get your median, to get the number of class, the frequency, and so on and so forth. Basically, that is the same thing here. So, but this one they use that. This one is a vector diagram. So this vector diagram is normally used to analyze the magnitudes and the currents and the rest, the size of the current, the size of the voltages in an alternating current, and the phases of them. I hope you are getting it.
Yes, sir.
Yes. Now, by convention, when we say by convention, usually the current phasor is drawn horizontal. So normally the current phasor is drawn horizontal, and the voltage phasor with a phase angle measured in and an anti-clockwise direction is taken to be the phase lead. And so normally when we are doing the phasor diagram, normally the current is drawn horizontal. That is basically what they are trying to say. The current phasor is drawn horizontally, and the voltage vector with a phase angle measured. When we get to there, we will explain all these things. Now we are going to consider three main components in an AC circuit that we are going to talk about. That constitute the circuits. Three main components. Now we have the resistors, we have the capacitors, and we have the inductors. We have the resistors, we have the capacitors, and we have the inductors. Now when we talk of resistors, you know resistors do oppose. They offer opposition to the flow of current, the alternating current. Now the capacitors also store current. Now the inductors, they are like the solenoid, so they store current in a magnetic field. They store energy or electrical energy in a magnetic field. Basically, that is it. So we are going to talk about this thing, and we are going to talk about both of them, their circuits. We are going to talk about the pure resistance circuit. If you have a pure resistance circuit, that means if you have a pure circuit that consists of only resistors, how it's going to behave. Then we are also going to talk about when you have all capacitor circuits, when you have circuits that is made up of only capacitors. We are also going to talk about when you have that when it's made up of only inductors. And so basically that's what we are going to do. So the three components we are going to talk about is please let me first of all type the definition of the distance. It's the phasor diagram. I said is a diagram which is used to analyze AC circuits. Now the three components we are going to talk about. We said we are going to talk about the resistors. I hope you know the symbol of a resistor. I'm going to talk about the capacitor. Uh, Capacitor. I'm going to talk about the inductor. I'm going to talk about the inductor. So that's it. And I hope you know the symbols for all of them. If you don't know, let me just write. Now, one symbol for a resistor is like this. And it is made in ohms. Then the capacitor is, so that is it. So this is farad. And the inductor, this is how the symbol for the inductor. That's a coil of wire. It stores electrical energy in a magnetic field. So this one is Henry. This one is made in Henry. Are we there? Now let's take them one by one and talk about them. So I'm going to talk about the pure resistance circuit. Types of AC circuits. So types of AC circuits. Type of AC circuit. Now the first type of AC circuit we are going to talk about is I said we have three main types of AC circuits we are going to talk about. We are going to talk about the pure resistance circuit. We're going to talk about the pure capacitor circuit. And we're also going to talk about the pure inductive circuit. That means the circuit made up of inductors only. So now we are going to talk about the pure circuit. Now, under this, only resistors are present, or only a resistor is present. Now, the voltage and the current rise and fall together. In this circuit, the voltage and the current always rise and they fall together. So both the voltage and the current, they all rise and they fall together. And because they all rise and they fall together, there is no phase. There's no phase between them because they all rise and fall together. So we all rise and fall together. There's no phase between us. So there's no phase difference. There's no difference in phase. I don't know how to explain the phase this thing. Let me check a complete dictionary this thing of phase so that I will know how to. If it was, I don't know if I'm right to say parts. Let me use this thing. So we are trying to say that in the resistor circuit, the voltage and the current rise and they fall together. They are said to be in a phase, and hence there is no phase difference between it. They are said to be in a phase. That means they are all in the same phase, or in other words, we can say in the same plane. And hence there is no phase difference. Now, when we say phase, let me explain what a phase is using the dictionary. A part or a step in a process, one part in a series of related events or actions. And so, for instance, we can say in batches, if we were to use the normal distance, but here we are talking about phase, like maybe there's no difference, they are all in one phase. Let me see, they are all in one plane. I don't know how to explain so that you get it. Or they are all in one form or one category. Let me put it that way. And so that is why, just because they all rise and fall together, and so they all rise and fall together, so they are in one phase. And so a typical diagram of it is this. And so this is an AC. Please, this AC is written like this. There's a symbol for AC. So you can just do it this way. You can do it this way. Some also want to put it in a circle. So when you see this is an AC current. DC is DC. This AC because it is moving in only one. It is sinusoidal. So that's how it works. And so if you have a typical resistor circuit, so it is made up of a resistor connected to the AC, connected to the AC. Connected to the AC. So that is it. And so maybe here can be the voltage across the AC. So we are seeing at the phase diagram, the current and the V, they are in phase. That means they are in the same plane. And so that is how it looks like. So the phase diagram, when we talk of the phase diagram, we are talking about a vector diagram. And so with a vector diagram, that is how it looks like. They are all in one phase. So if here is current, here will be, let's say, voltage. So there's the voltage of the resistance and there's the current of the resistor, because here you are talking about resistance circuit. And so here both of them are in one phase. That is why they are all on a single line, because they are all in one phase and they are all using the same trajectory. When I say trajectory, they are all using the same route. So realize that they are all moving along. So they all go, they all come, they all rise, they all fall. That is it. So because of that, there's no phase angle. Now there's a phase symbol for a phase angle. Because of that, there's no phase angle. So here the phase angle between this is 0, because they are all in the same phase, or they are all in the straight line, or they are all in the same line. Let me put it that way. And so as a result, it is 0. It is 0. Now we can relate resistance, the resistance using the root mean square. We can relate the resistance to be equal to R is equal to our VRMS. All over I R M S. And so that is it. If you want to use, for instance, if you are to draw, because if you are using the sinusoidal this thing, when you want to relate them, so here's how the sinusoidal looks like. Here's how the sinusoidal looks like. Here's how the sinusoidal looks like. Now, so for instance, if I have if the first one, this one is V, the peak of this is this I, and this one is V. That means we are representing the reactions of each of what we call it, the voltage and the current, on just a single diagram, or just on a single graph. That is basically what we mean. And so this is I naught. And so this one, the first one is the peak of the current, and this one is the peak of the voltage. Now, when we want to relate them in terms of their resistance, we can say resistance will be equal to V naught all over I naught. I naught. Are we there? Hello, are we there?
Yes, sir.
Yeah. And you know, this one is gotten from, when we are using this curve, this one is gotten from, because of the sinusoid, I taught you that here the VRMS, V, or V, or it can be VRMS, will be equal to V naught, because they are sine. This will be equal to V naught sine. Someone should check sine 0. Sine 0. Let me see. And we are going to get
Size 0.
0. So and we are going to get I is equal to sine. So when you still use this, you are still going to get what I've written on top. So our resistance will be equal to V naught sine omega t all over I naught. I'm just showing how this one came about. V naught all over sine omega t. You know that this and this are equal, so this or are the same, so this and this will cancel. Now when this and this cancel, we are going to get R is equal to, this. Please, now do you understand how it was derived? So
Yes, sir.
so V naught can be equal to I naught times R. We are not bringing R because we don't have resistance, peak resistance and the rest. We are not talking about, just talking about this in terms of their peak. It is just a proportionality constant. When you do Ohm's law, resistance is a constant. Listen. So basically, that is it. Now, in terms of power, if we want to relate them in terms of power, it will still be the same thing we did. In terms of power, it will still be the same. Power is equal to current I naught V naught sine squared omega t. I hope we've done this, Dada. And we've not. So the power dissipated in a resistor will be the current times the voltage. And when we are to use this, and because it's sinusoidal, when we are to use this, we are going to multiply this times this. When we multiply this, and we are going to get V I naught. This and this will multiply, so it will be sine squared omega t. And that will be the power of current, the power, what do you call it? The power dissipated in a resistor. So the power dissipated in a resistor will be equal to power. The formula for power is constant, I times V. But our I, which is our effective I, in other words, our root mean I, is equal to the whole of this. Then our root mean voltage, root mean square voltage, V is equal to the whole of this. And so to find for power, we multiply the two of this. We are going to get V naught I naught sine squared. So this will be the power of heat, or the power dissipated, the power dissipated in this circuit, and you know this is a resistor circuit, so we are talking about the power in the resistor circuit. Please, I hope I've made myself clear. Or if I haven't, please tell me, so that I understand. So basically that is it. We have just here, Ruben, talk to me.
So please, for the power, will the omega and the time be also squared?
You said the power, will I use what?
Will the omega and the time be also squared?
No. The squared is affecting both the omega and the time. This is in what do you call it? This is in trig. This is in trig. So when you're multiplying this, we consider this to be an angle. And a trig. We consider the whole of this to be an angle. But because of the nature of what we are doing, so here could have also been 2 pi f this thing. So when you multiply, so it is more or less like this. If you are considering this to be an angle, so it will be more or less like sine theta times sine theta. What are you going to get? Sine squared theta. Are we getting it? Hello, Ruben, you get it?
Yes, sir.
So we consider this to be, you know, when we talk of sines, we are talking about angles here. So and the rest, we are talking about angles here. So basically that is it. So sine times sine theta, so just represent this by theta. And when I'm multiplying, you get sine squared theta. So the squared it affects everything here. It affects everything here. If it was to be in the differentiation, that would have also been a different story altogether. Asa, you want to talk? Please talk to me. So we just have some 4 minutes. I don't want to teach any new topic. Otherwise, man, not finished. So that is it. Next time, I'm going to look at the pure capacitor circuit. Please, you also read before you come in, so that we all share ideas and we are good to go. And another pure capacitor circuit, we are going to look at the capacitive reactance, which is XC. So we are going to look at that. That is it. We are please, there's a message circulating that you guys are going to school on the 6th. It is false. Please, it is false. According to the GS, the report on when you guys will resume school will be submitted on the 21st of September. That is it will be ready by 21st September. So they can only communicate the day you guys will go to school after 21st September. Are you getting what I'm trying to say? and it's just because it is assumed that by 18th
Yes.
September, by 18th September, all the the WASI students would have completed. They want everyone to complete because definitely you know that you can't just go and add up to those there. You will have to wait so that they all come. They'll go and spray the place and so on and so forth. Before if they'll open you guys in March or they'll let all of you guys at home go out, they'll do. But they'll have to spray there and all this, so they can't let you also go and join. Already they're even thinking about how to when they are coming home, how they are going to do it, whether they'll come in batches and so on and so, because there are some schools they are affected by the coronavirus. They were affected, so, and they don't want them to come home and come and infect their parents. So they'll have to check all those things, whether they'll do them quarantine and see that they are all fine, test them or something. So a lot will go into it. And so latest by 21st, it will come. So you can only know. I know hopefully, definitely by October that you guys will go to school, but not September. So please take note. Don't be this thing. Don't let anyone lie
Yes.
you. And please, you guys should read. I'm very tired. I want to teach early in the morning at Kaswa. I just came. So I'm tired. But we've done our normal time now. So please, if you don't understand anything, kindly PM me and let me explain it to you. Eh? But not right now. I want to sleep small. So that's it. Yeah, Ruben, talk to me. You meet at 4:30, and Ruben, you meet at 4:30.
Don't forget to upload
I
the
will.
videos
I will, Ruben. I will. Please, those of you who are owing me, please, I need money. So come and give me some small coins and let me also eat. Have a wonderful day. I love you guys all. God bless you. Next week, your sisters or your seniors will be coming home. Next year, by now, you also be preparing to write or you'll be writing. So please know that uh, it's just around the corner. So please study hard. All right.
Yes,
Uh,
sir.
Thank you.
Thank you, sir.
You're welcome. Bye. Could reset this game. Onseklin said that the knockout ties have been more exciting and the format has changed to allow the competition to be completed in a shorter span after the COVID-19 pandemic.